Until now, we've been talking about the very basic kind of direct proof, but sometimes direct proof can get a little more complicated, and we have to sometimes use a few different cases in the proof, right? So using cases is a type of direct proof, um, but it involves breaking down breaking down breaking down something into a few different cases and then proving each case separately. So here's an example. We have a proposition. If n is a natural number, then 1 plus -1 to the power of n times 2n minus 1 is a multiple of 4. That's what the proposition says. So we're going to try to prove this using direct proof. So we'll start off by supposing n is an element of n, right? So in other words, we suppose that this if is true, and our goal is to show that this is true, meaning to show that this number is a multiple of 4. But it doesn't seem like any obvious way to do it. Like just the fact that we know n is an integer, or rather a natural number, how is that going to show us that this is a multiple of 4? So what we have to do is, in this case, is break down this into two possible cases. Now, so in general, you might have 3 cases, you might have 4 cases, but it's very common to break it down into 2 cases. But it all depends on what you on the particular problem, and you'll see as you do the homework. So here's how we're going to break it down. Well, if n is a natural number, then obviously n has to either be even or odd. Every natural number is either even or odd. So n is either even or odd. So let's break down this situation here into 2 cases. So case 1 is where n is even. So what we're going to do in case 1 is show that if n is even, then this is a multiple of 4. Then we'll go on to case 2, and case 2 will deal with the case where n is odd, and we'll show that there too, this is a multiple of 4. And that will allow us to prove the entire proposition, because the proposition is talking about a natural number. Every natural number is either even or odd. If we prove in both cases that that this thing is a multiple of 4, that will have proven the proposition. So let's do case 1. Case 1 says n is even. Okay, so if n is even, let's use that to our advantage. Let's write it as n equals 2 times k for some integer k. Okay. Now, what else do we know? Well, if n is even, then what is -1 to the power of n? Okay, it doesn't matter what n is, but if n is even, then -1 to the power of an even number is going to be 1. Again, -1 multiplied by itself an even number of times, right? That's 1. Right, so like -1 squared is 1. -1 to the power of 4 is 1. Okay, so that's since n is even. All right, so now let's try to figure out what this turns out to be. Again, all talking about where n is even. So thus, 1 plus -1 to the power of n times 2n minus 1, let's rewrite this as, so 1 plus 1 times, right, so this -1 to the power of n turns into a 1, and then the n turns into 2k, right, so we have 2 times 2k, 2n, 2 times 2k minus 1. That simplifies to 1 plus 4k minus 1, or 4k. Now 4k is obviously a multiple of 4, because why? Because 4k means 4 multiplied by an integer k. That's a multiple of 4, right? That's how multiples of 4. What does a multiple of 4 mean? It's 4 multiplied by some integer. So that's 4k. Great. So that has to be a multiple of 4. So we're done with case 1. Again, in case 1, what we've shown is that if we suppose that n is even, then this thing is a multiple of 4. We have shown that, but we're not done the proof, because the proposition never claimed that n has to be even. It said n just could be any natural number, so either even or odd. So we've shown that if n is even, that this has to be a multiple of 4. But what if n is odd? So we have to do that now in case 2. So let's continue the proof. So here's a continuation. Case 2 is where n is odd. So if n is odd, n is equal to 2 times k plus 1 for some integer k. Now you might object here, how can we reuse k? How can we reuse k? Haven't we used it already for a different context? Right, we've used it for n equals 2 times k for, so in other words, how do we know that it's the same k as before? Well, the answer is we don't. And the thing is, each case is like its own independent proof. So it's kind of like, I'm not really reusing it because it was used in a different proof. When we used it on the previous slide, it was used in sort of a different proof, because each case is like its own mini proof. Right, so we could reuse k. If it makes you uncomfortable, you could use j here instead. Okay, so since n is odd, n equals 2k plus 1. Also, since n is odd, -1 to the power of n is going to be equal to -1. Right, -1 raised to any raised to any odd number, raised to the power of any odd number is going to be -1. Okay. Actually, I should say raised to the power of any odd positive number, right? We're only talking about natural numbers here anyway, so we're only talking about positives. Okay. Now, so thus 1 plus -1 to the power of n times 2n minus 1. So the -1 to the power of n will just become -1. Now the n will become 2k plus 1. So we have this 1 plus -1 times 2 times 2k plus 1 minus 1. Okay, let's simplify this. So let's first multiply out the 2 times 2k plus 1. So we have 4k plus 2 here in that place. And now let's simplify this parenthesis. So we have 1 plus -1 times 4k plus 1. We'll multiply the -1 by each of the things inside. So we'll have 1 plus -4k minus 1. In other words, 1 minus 4k minus 1. In other words, -4k, right? The 1 and the -1 cancel each other out. Now, -4k can be written as 4 times -k. 4 times -k. Right here we're just, this negative here is like -1, like a multiple of -1. So I can move it further on. Okay, so we have, now this thing here is a multiple of 4, right? It's 4 times an integer. How is this an integer? Well, k is an integer. -k also has to be an integer. No matter what k is, -k is also going to be an integer. And we're doing 4 times that integer. So that has to be a multiple of 4, because that's what a multiple of 4 is. It's 4 times any integer. Okay, now let's conclude the proof. Since our two cases cover all possibilities for a natural number n, and in all cases we've shown that 1 plus -1 to the power of n times 2n minus 1 is a multiple of 4, we conclude that the proposition is true. Okay, because we've broken down n into into a situation where we have cover all possibilities for n, and in all of those possibilities we show that the proposition is true. So therefore, we conclude that the proposition is true in all cases. But part of the difficulty with this kind of problem is knowing how to break down the cases, and there is no clear guidelines. There's no clear formula to tell you what to do, and that's generally the case with doing proofs. We'll get to more complicated kinds of proofs. It's hard to know ahead of time what kind of proof will work, what kind of proof won't work. I mean, you do get some sense after doing a certain number of examples. You do get some sense of what might work or what might not work, but there is no foolproof way of knowing what's going to work ahead of time, what's not going to work. So sometimes you have to try different ways. Okay. Now that we're talking about using cases, let's introduce a new definition, and let's do a proof involving cases involving this definition. So this definition is parity. You may have heard this definition. So two integers have the same parity if they are both even or both odd. Okay, so meaning they're not the same, they're not necessarily equal to each other, but they have the same parity, both even or both odd. Otherwise, they have opposite parity. So like if the first integer is even and the second is odd, or vice versa, then the two numbers are said to have opposite parity. So this is a definition that involves integers, because we only talk about odd and even when we're talking about integers. So this is a definition involving integers, and we have same parity or opposite parity. For example, 3 and 27, those are integers. They have the same parity because they're both odd. The integers -8 and 60 have the same parity because they're both even. 3 and 24 have opposite parity because the first one is odd and the second one is even. The integers 0 and 3 have opposite parity because 0 is even and 3 is odd. Okay, so that's the same parity. That's what parity means, or same parity, opposite parity. Now let's do a proposition and prove it. If two integers have opposite parity, then their sum is odd, right? So that means if we have m and n being two integers with opposite parity, then we're going to have that m plus n is going to be odd. That's what this is claiming. That's what the proposition is claiming. So let's prove it using cases. Now, how did we know to prove it using cases? Well, because it does seem like a natural fit, because when we have two integers with opposite parity, that breaks down nicely into two cases where the first is odd and the second is even, or the first is even and the second is odd. So proof. Suppose m and n are two integers with opposite parity, right? Now, it doesn't seem obvious to know what to do next. If we were trying to just do a plain basic direct proof without using cases, what would we do next? M and n are integers with opposite parity. Okay, how do we know that the sum is odd? How do we know that m plus n is going to be odd? So what we're going to do now is break this into cases. Case one is where m is even and n is odd, right? So if they have opposite parity, that means one is even and one is odd. So let's first deal with the case where the first one is even and the second one is odd. M is even and n is odd. Okay, so if we know that m is even, m is equal to 2a for some integer a. Also, since n is odd, we know that n is equal to 2 times b plus 1 for some integer b. Keep in mind, we cannot reuse a here. We cannot say 2a plus 1 here, because this 2a, in other words, m is equal to 2a, but that's not necessarily the same a that we're using for n. So in other words, for example, let's say m is 4. So then this would be 2 times 2, okay? But let's say n is 10. Let's say n is 11, right? It has to be odd. So let's say n is 11, then this b would be 5, not 2. So in other words, you cannot make the assumption that this a and this b are the same. So that's why we give them two variable names to account for the possibility that they're different integers, that they're different. Okay, so we have m is even, n is odd, and we have m is equal to 2a and n is equal to 2b plus 1. Now, what are we trying to show? We're trying to show that the sum of m and n is odd. In other words, what is m plus n? Well, let's see. M plus n is equal to, well, 2a plus 2b plus 1, right? 2a plus 2b plus 1. That can be written as, we can factor this as, we can factor the 2 out of these two terms, right? Again, our goal is to show that this thing is odd. So we can do that by factoring out the 2 from both of these terms. So we have 2 times a plus b, and then the plus 1. This is an odd number because it's the form of an odd number. It's 2 times an integer plus 1, right? A plus b has to be an integer because a is an integer and b is an integer. So a plus b has to be an integer. So that was case 1. That's where m is even and n is odd. But now we have to do with case 2. Case 2, let's say, is where m is odd and n is even. So notice case 1 and case 2 together will cover all possibilities, because if I have m and n are being two integers with opposite parity, then I must have either that m is even and n is odd, or on the other hand, I must have that m is odd and n is even, right? So those two cases cover all possibilities. Okay, so if m is odd, that means that m is equal to 2a plus 1 for some integer a. So just wanted to say, even though we seem to be reusing the same letter that we used before, it's not really doing that, because each case is like its own mini proof. So we're done with the case one. So we're done with that mini proof, and now we're starting a new mini proof, and so it's independent. So each case is considered independent from the other cases. So we could reuse variable names, although you don't have to. If you want to use 2c plus 1, that would be fine. Since n is even, n is equal to 2b for some integer b. Now, what is n plus n? Thus, n plus n is equal to 2a plus 1, right? That's m, 2a plus 1 plus 2b. Well, this can be written as 2 times a plus b plus 1, which is odd. We see that in both cases, which together cover all possibilities, that m plus n is odd. So we've proven the proposition. If two integers have opposite parity, no matter which way they work out, whether it's case 1 or case 2, their sum is odd. M plus n is odd. Okay. Now notice here in this proof that the two cases were extremely similar to each other, right? They're really, really similar. It's just the order of m and n were reversed, but there was no significant difference between them, right? So there was no we didn't have to treat each of them in different way. Basically, they were the same thing, but just the order was different. So in such a situation, you'll have some books talk about this idea of without loss of generality. So let me explain. So there's a convention in math, which is, I think, a bad convention, but it is a convention. Sometimes when the cases of a proof are very similar to each other, as in here, right, where the two cases are very similar to each other, some books will only write out one of the cases and use the phrase without loss of generality to include the similar cases. For example, let's say for the previous proof, you might have a book write the following, right? So again, for the previous proof, which were both parts were very similar to each other, just the order of m and n was different. In other words, which one is even and which one is odd, that was the only difference. So you might start such a proof by saying, suppose m and n are two integers with opposite parity. And then here the book might say, without loss of generality, suppose that m is even and n is odd. So what they're trying to say here is that, yeah, let's suppose that m is even and n is odd, but this will also work if it's the other way around. So without loss of generality means that this will also work for other cases. But I'm not going to spell out those other cases for you. That's what it means. So suppose that m is even and n is odd. Since m is even, we have m equals 2a. Since n is odd, we have n equals 2b plus 1. Thus, m plus n is 2a plus 2b plus 1, which is 2 times a plus b plus 1, which is odd. Okay, so that would be the whole proof in many textbooks, right? They wouldn't bother giving you the other case because the other case is so similar to this case. And they would use this phrase without loss of generality to indicate to you that they're really not spelling out the other case or cases. Now, you might be tempted to do the same when writing your own proofs. You might be tempted to not write out all the cases. However, that's a very bad idea, in my opinion. So it is not a good idea to use this style when writing your own proofs, since it is easy to mistakenly believe that cases are similar when they really aren't. So in this particular example that we were just doing, the cases were in fact really similar. But sometimes it looks like cases will be similar, but when you actually get into the cases, you see that they're actually not too similar at all, and you have to deal with each of them in different ways. So if you try to, it's a big risk to try to use this style, to say without loss of generality and only spell out one of the cases. And you should, if you do it, you should only do it when you're absolutely confident that the two cases are extremely similar to each other. But really, I would say it's generally not a good idea to do it on your own, to do this kind of stuff on your own, but you should be aware of it because you'll see it in this book or in other math books. Now we're done with chapter 8. So we're done with the topic of direct proof and including the idea of using cases. And now we're going to go on to chapter 9, which is talking about contrapositive proof. That's the topic of chapter 9, and that will be another video or maybe 2 videos.